Alright, so moving on to our Unit 2 review here. First and foremost, basic definitions. Forces are simply pushes or pulls. We really don't need more of a formal definition than that. And all forces are caused by objects. Okay, that's an important one. There is no force of inertia, force of momentum, force of speed, things like that. Moving on to Newton's laws, the first one is that unbalanced forces cause acceleration, and that is key. Forces don't cause motion or velocity, they cause acceleration. If we have no unbalanced forces, right, there's two possibilities. It either means that we are traveling at a constant velocity or we are at rest. Either one of those is acceptable. We're just not accelerating. We're just not changing our motion. But if we're already in motion, there's no unbalanced forces, we're going to continue in motion. Second law is really just the equation, F equals ma, but it does tell us that mass and acceleration are inversely proportional, and that force and acceleration are directly proportional. And the third law is that forces come in equal and opposite pairs. Okay. Another way of looking at that is you can't push something without it pushing back equally. Keep in mind that these third law pairs, as we call them, do act on different objects. So if we have the force of A on B and the force of B back on A, those are your third law pairs. Those are the forces that are equal and opposite. Lastly, some tips for solving. Again, these are things that should be thoroughly ingrained in your head. We're always going to set up max and may. That's a big one. All right, you guys know that at this point. We're always going to draw our free body diagram. All right. Of course, you're going to be careful with signs, especially of force and acceleration. We want to make sure we're consistent with those signs. All right. And lastly, we're going to break into components any angled forces. All right. Much like projectile motion, we can view the x and y direction as two separate things. Okay. And so we're going to split them up into two problems, basically. All right, moving on to some specific forces. First one we have is gravity. As you know, that always acts down, and we can calculate that with Fg equals mg. All right. Normal force, there's no formula, but that's always going to act perpendicular to a surface. And that's a force that its amount is going to depend on what other forces are present. Moving on to friction, we have two types. Okay, so this kinetic friction is for sliding objects. Okay, and it's going to oppose the direction of velocity. All right, or the direction that the object is sliding. All right, and the way we find kinetic friction is force of friction is equal to mu k times our normal force. All right, kinetic's the easy one because it has a definite value. All right, we know it's always going to be equal to mu k times our normal force. Static friction is going to be the not sliding case. All right, this is going to oppose the direction that the object wants to move. And the way we find it is FF is going to be less than or equal to mu s times Fn. So we keep in mind that this term here, mu times the normal force, is going to give us our maximum force of static friction. All right, moving on to inclines. Remember, with inclines, our trick here is we're going to tilt our axis. Okay, that's the key. In terms of our forces, we have the force of gravity, of course, acting straight down, but because we tilt our axis, we're going to break that up into the y component, Fg cosine theta, and the x component, Fg sine theta. And that just comes from the fact, the reason why it's like that, sine and cosine, is that the angle of the incline ends up being this upper angle here. Additionally, we always have the normal force, and there could be other forces, pushes, pulls, etc. But those are the main forces that we have, the ones that we're always going to have when an object's on an incline. Lastly, we have the spring force. And with the spring force, it's given by Fs equals Kx, where K is our spring constant and X is the distance stretched or compressed. Okay, this force actually plays an important role later on when we get to simple harmonic motion, as you now know, because the force is proportional to the distance, and therefore it is a case for simple harmonic motion. All right, last thing, this would be setting up the equations or the situations where there's more than one object. So the two things we're always going to know when two objects are accelerating together is they're going to have the same acceleration. And this idea was expanded upon when we got to the rotational unit, looking at situations where there was linear and angular acceleration together. But if we're ignoring rotational stuff, it's just two objects moving together, they're going to have the same acceleration. And we also know the force connecting them, okay, the force between them, whether it's them actually pushing on each other or maybe a rope and there's tension between them, is also going to be the same. So when we're doing these problems, we're going to set up F equals ma for each. We may need to do both max and ma, maybe just one of them. It all kind of depends on the situation. Okay. We want to be careful, especially in these problems, with our signs. What I always do, the trick that we've talked about throughout the year, is make the direction of acceleration always be the positive direction. And base all your other forces off of that. It makes things work out mathematically a little bit easier, but certainly you don't have to do that. You do have to, though, account for situations where maybe gravity is going down, you make that negative, and then the acceleration is also down. You need to be consistent and make that negative as well. And the last thing to keep in mind here, and this is partially a conceptual idea, but also a trick that could be of use to you, is we can always treat as a system. All right, so we don't have to, but we can treat as a system. And if that's the case, okay, we ignore forces between the objects and only consider outside forces. And when this happens, we're also going to use the total mass of all the objects in our system. Now, our way of setting up individual F equals ma equations and free body diagrams ultimately leads to this, right? When we set up that system, it should simplify to this situation where the forces between the objects cancel and we're left with the total mass.